All right, how's everybody doing today? We're going to talk about predicate logic, rules of inference. So we're adding on to what you already know. In previous chapters, we've introduced the rules of implication and the rules of replacement. Now that we're doing predicate logic, we need some additional rules. So we're going to talk about 5 new rules in particular. One is universal instantiation, which we abbreviate with capital letter U and I. 2 is universal generalization, which we abbreviate with capital U and capital G. 3 is existential generalization, which we abbreviate with a capital E, capital G. 4 is existential instantiation, which we abbreviate with capital E, capital I. And then last but not least, we have what we call the change of quantifier rule. Sometimes you'll hear me refer to it as quantifier exchange. And its abbreviation is capital C and capital Q. So I'll go through each one of these rules. We'll do a few examples, and then we'll call it quits. So here we go. First things first. Universal instantiation in general. Here's a general rule. Universal instantiation is an operation that consists in deleting a quantifier and replacing every variable bound by that quantifier with the same instantial letter. Now remember what your quantifiers are from the last section, which is your existential quantifier and your universal quantifier. This is the quantifier that we're talking about in this particular definition. So here's how it goes. For all x fx, if I instantiate it, I can remove the quantifier and replace it with another variable or the same variable. Let me back it up for 1 second. Universal instantiation is an operation that consists in deleting a quantifier and replacing every variable bound by that quantifier with the same instantial letter. So notice what happens here. Just look at the example on the left. For all x fx fy, I delete my quantifier, which is the all x right here. I have my arrow on it. Delete this, and then I can replace the variable that is bounded with another variable, or if I would like, with a constant. So again, we can replace the bound variable with either another variable or a constant. Now remember, your constants are your lowercase letters a through w, and your variables are x, y, and z lowercase. So with universal instantiation, the notion is that I can remove my universal quantifier, hence the name universal, remove my universal quantifier, and then replace my variable with either another variable, the same variable, or a constant. So let's look at some examples. All guitarists are rockers. Jimi Hendrix is a guitarist. Therefore, Jimi Hendrix is a rocker. Now we can symbolize this as follows. Hopefully you remember this from the last section. For all x, if x is a guitarist, then x is a rocker. Premise 2, Jimi Hendrix is a guitarist. Now hopefully this is familiar with you at this point. But remember, what we have going on here, because it says all guitarists are rockers, is a universal statement, which of course we symbolize with a universal quantifier. And remember, all our universal statements are going to be displayed as conditionals. My second premise, Jimi Hendrix is a guitarist, is a singular statement because it's about a person, place, or thing, mainly Jimi Hendrix. So that is represented by capital G for guitarist as our predicate, and then lowercase j for Jimmy. My conclusion in this case is therefore Jimi Hendrix is a rocker, which we display as capital R for rocker and lowercase j for Jimmy. Okay? Now in order to solve this, we're going to need to use our universal instantiation. Now before that, let's look at a few things. The first premise states that for any item x in the universe, if that item is a g, then it is an r, right? For all x, if x is g, then x is r. So for any item x in the universe, if that item is a g, then it is an r. Since Jimi Hendrix is himself an item in the universe, the first premise implies that if Jimmy is a g, then Jimmy is an r. A line stating just this can be derived by UI. So universal instantiation provides us with an instance of the universal statement for all x, if gx, then rx. So let's take a look at how this will work. So here it is again. For all x, gx implies rx. There is a j that's g, therefore jr. First thing I'm going to do, UI. Remember, what's UI allow me to do? It allows me to remove my quantifier and then replace the variable, the bound variables, with either a constant or another variable or the same variable. In this case, since my conclusion is a constant, I'm going to replace these variables with constants. And I'm going to choose j because ultimately that's what I want to derive. Furthermore, if you look at line 2, you'll see that I have the antecedent to this conditional. So what rule can I use? Hopefully you said modus ponens to get my rj. So this proof is complete. All I had to do was UI my universal statement, which means I remove my quantifier and replace my variable with either a constant, another variable, or the same variable. And in this case, I chose constant j. And then now that I did that, I can do modus ponens. I cannot do modus ponens from here to here. From line 2 to line 1, I cannot do modus ponens. Why? Because this is not the main operator. The main operator in this particular statement is the universal, or at least we can view it that way. This universal quantifier governs the entire conditional. Okay, so I have to remove this quantifier in order to use my rules of implication. We'll talk more about this in a little bit. But right now, just try and get the idea that the way you use universal instantiation is to remove the quantifier and replace the variable with either constant or a variable. So in this case, I derive line 3 via UI from line 1, and then I can use line 2 and line 3 modus ponens to get the rj, which is exactly what I was trying to get. Now let's look at rule number 2, universal generalization. Now notice, there's a restriction to universal generalization. We can go from a variable to a variable, but not from a constant to a variable. Further, in contrast to UI, UG, rather than removing a quantifier, actually adds a quantifier. So what we do with universal generalization is we take a statement function. Remember, statement functions are what are left over if we remove a quantifier or if there is no quantifier. We take the statement function and we quantify it. So in this case, I have statement function fy. I can quantify it to say for all x, fx. What I am not allowed to do, hence the reason this is in red, is go from a constant to a universal. And there's a few reasons for this. One is that just because there's an individual A that is an F, which is what this says, remember this is a singular statement, so what I'm telling you is that there's an A that's an F. So for instance, maybe A stands for atom and F stands for fantastic. I'm claiming atom is fantastic. That does not mean that everything in the universe is an F. So in other words, just because atom is fantastic doesn't mean that everything that exists is fantastic. So when you're doing universal generalization, never, ever, ever can you go from a constant to a quantified variable. What you can do, though, is go from one variable to a quantified variable. Remember, again, our variables are lowercase x, y, and z. So if I have fx, I can go to for all x, fx, or for all x, fy, or for all y, fy, or for all z, fz. In this case, I have an fy, and I went to for all x, fx. If I wanted to, I could have gone to all y, fy. Okay? But just don't forget, you cannot universally generalize a constant. You are only allowed to universally generalize a variable. So let's look at an example. All rockers are crazy people. All crazy people are out of control. Therefore, all rockers are out of control. We can symbolize this as follows. For all x, if x is a rocker, then x is crazy. Number 2, for all x, if x is crazy, then x is out of control. Therefore, for all x, if x is a rocker, then x is out of control. Now, you might think right off the bat that you can do hypothetical syllogism here. But remember what I said earlier. We cannot use our rules of implication on lines that are completely governed by a quantifier. Remember our talk about bound versus free variables at the end of the last podcast. In this case, on premise 1, we should recognize that both our variables are bound by this quantifier. And same in premise 2 and same in the conclusion. Everything within these parentheses is bound by this quantifier over here in premise 1. So that means that in order for us to use our rules of implication, we've got to remove these quantifiers. Once we UI lines 1 and 2, we can then perform hypothetical syllogism. But in order to reach our conclusion, we will need to reintroduce the universal quantifier, and this is what UG allows us to do. So remember, with universal instantiation on premise 1 and premise 2, I'll be allowed to remove these quantifiers. But notice my conclusion is a universal statement. So in order to reach my conclusion, I'm going to have to reintroduce my quantifier, which is exactly what UG is going to allow me to do. So let's take a look at the example. Premise 1, for all x, if x is r, then x is c. Premise 2, for all x, if x is c, then x is o. Therefore, for all x, if x is r, x is o. First things first, I'm going to UI premise 1. So I'm removing the quantifier, my universal quantifier, and I'm replacing my variable with a variable of my choice or a constant. In this case, I'm going to replace it with a variable. And why? Because ultimately my conclusion is a universally quantified statement. And remember, when we're using UG, and I'll back it up just for a second. When we're using UG, we're not allowed, right, to go from a constant to a variable. We have to go from a variable to a variable. Okay? Now, because we have to go from a variable to a variable, it makes sense that we would, when we UI line 1, that we switch the variable to another variable. That way, when it comes time to UG, I'll be allowed to do it. If I had switched this to a constant, for instance, if it had RA, then CA, I would not be allowed to UG, and therefore I would have no way of getting back to this conclusion. So let's follow along with it again for a second. Second move, I'm going to UI line 2. Now what can I do? Well, now that I have removed the quantifiers from both line premise 1 and premise 2, I can use 3 and 4 to do a hypothetical syllogism. Notice what it says. If RY, then CY. If CY, then OY. Therefore, if RY, then OY. Via 3-4 hypothetical syllogism. All right, now notice, my conclusion is a universally quantified conditional. Rx implies Ox. So what can I do to line 5 to get this? Well, I can use my UG. I can add a quantifier to it and change this variable to match this quantifier. Now notice, if my quantifier here was a y, I would have to keep my variables as a y. But since I ultimately want for all x, if Rx, then Ox, I'm going to use the x quantifier, and when I UG, I'm going to change my variables from y to x. Okay, so this problem would be solved. Moving on, let's look at existential generalization. Existential generalization, much like universal generalization, is going to be involve adding a quantifier. However, as you might guess, in this case, instead of adding a universal quantifier, we're going to add an existential quantifier. So let's look at both these instances. In this case, I have a constant, and in this case, I have a variable. Let's look at the constant first on the left. So I have FA. I can existentially generalize this by adding a quantifier to it and changing my constant to a variable that matches the variable in my quantifier. Same thing here. I have Fy. I can add an existential quantifier and then change my variable to match whatever the variable is in my existential quantifier. So note, we can replace a variable or a constant with a bound variable when we're using existential generalization. Unlike UG, where I could not go from constant to variable, with EG I can. And there's a reason for this. Notice what it says. There's an individual A that is an F. Looking at my left over here, there is an individual A who is F. So again, let's think that A stands for atom and F for fantastic. So I'm saying atom is fantastic. Well, that means there's at least one thing in the universe that is fantastic, which is exactly what is said here. There exists an X such that X is F. So if F stands for fantastic, then this statement here would say there exists an X such that X is fantastic. We know there exists at least one X that's fantastic because we're telling you right here that atom is fantastic. Okay? So unlike universal generalization, I'm allowed to go from constant to variable when I'm doing existential generalization. So let's look at an example. All bass players are legends. John Paul Jones is a bass player. Therefore, there is at least one legend. We can symbolize this as follows. For all X, if X is a bass player, then X is a legend. John Paul Jones is a bass player. Therefore, there exists at least one thing that is a legend. Now note, if we instantiate the first line with respect to J, in other words, if I instantiate this line and change my variable to J, then we can obtain LJ via modus ponens. But if it's true that John Paul Jones is a bass player, then it certainly follows that there's at least one legend, namely John Paul Jones. This last step will accomplish by EG, existential generalization. So again, we'll use one of our previous rules to remove this quantifier. We'll use universal instantiation. We will change this variable to a J. Then we'll be able to take BJ into this and cash out an LJ via modus ponens. Then we will add in our quantifier. So let's take a look. For all X, if X is B, then X is L. J is B, therefore there exists an X such that X is L. First things first, we're going to UI line 1, giving me BJ implies LJ. Now that I've done this, it should be fairly obvious that with lines 2 and 3 I can do modus ponens. Right? If BJ, then LJ. On 2 I have a BJ. Therefore, I have an LJ. 2, 3 modus ponens. Now, we can use our rule, existential generalization, to get our conclusion. All right? I can add a quantifier and then change my constant to the variable that is encompassed in my quantifier. Thus, I end up with there exists an X such that X is L from 4 EG. Problem solved. Note, there's no restrictions on EG. The operation can be performed when the instantial letter is either a constant, as in the above example, or a variable. So we talked about this before. When doing EG, I can move from constants to variables or from variables to variables. In this particular case, the reason that I instantiated on line 3 to use a constant is because I had a constant on line 2. So if I wanted to do modus ponens and I wanted to be able to get there as quickly as possible, the easiest move was to take line 1, instantiate it, and use the letter J in place of my variable x. So here's a broad rule for generalization, or a couple of them actually. It's introducing a quantifier immediately prior to a statement function, or another quantifier. Now that's something we're not going to get to in this particular class, but note that if you were to get more advanced into logic, you would eventually see quantifiers inside of other quantifiers, but don't worry about that for now. We're only going to be using it to introduce quantifiers immediately prior to statements and statement functions. 2, replacing one or more occurrences of a certain instantial letter in the statement or statement function with the same variable that appears in the quantifier. So in other words, when we're replacing the instantial letter, we're going to replace it with the same variable that appears inside the quantifier. So let's back up for a second. Again, look here. The variable inside my quantifier is an x. Hence the reason I use an x here. Okay? If this had been a y, I would put a y here. Now let's talk a little bit about universal generalization versus existential generalization. I want to make a few points clear here. For UG, all occurrences of the instantial letter must be replaced with a variable in the quantifier. For EG, at least one of the instantial letters must be replaced with a variable in the quantifier. So remember, when you're universally generalizing, as in UG, every single occurrence of my instantiated letter must be replaced with the variable in the quantifier. I'll show an example of this in just a moment. And for EG, I'm only required to instantiate at least one of the letters, not necessarily all of them. So let's take a look at how this works. So these are both valid instances of EG. Let's say that I have a premise that says FA and GA. I can do one of two things here. Well, one of many things, but here's at least two examples of what I can do. Look to the left first. I can generalize across the entire line, right? Which means that I can substitute my variable x for the a in F and the a in G. So in this statement, what I'm saying is there exists an x such that x is F and x is G. That's a legal move from 1 EG. Okay? I can also do it this way, where I only substitute the variable for the F. Notice my G, I kept my constant. Now let's back it up for just a second. Look at the rule for EG. At least one of the instantial letters must be replaced with the variable, which is exactly what happens in the second example here. In this second example, I've only replaced one of the letters with my variable that's in my quantifier. Okay? And this is completely legal, so both of these are valid. In addition, I could have done the G and not the F. It could have said there exists an X such that FA and GX. As long as one of my letters gets changed to the variable that's in my quantifier, then EG is completely fine. Okay, backing up. Now again, for UG, all occurrences of the instantial letter must be replaced with a variable in the quantifier. So every single instantial letter must be replaced with the variable in the quantifier. So again, unlike EG, where I could replace one of my instantial letters with a variable and not the other, when we do, when we do UG, we have to replace them all. So look at number one on the left side over here. If I have FX implies GX, I can UG that to be for all Y, FY implies GY. But notice, every single instance of my instantial letter has been replaced by the variable occurring in my quantifier. Okay? So all of these are bound by this quantifier. Do not do this over here on the right. Hence the reason it's in red and I have this big invalid here. Invalid. Don't do it. Notice what was done here. We had fx implies gx, and we UG'd it to say for all y, fy implies gx. This breaks one of our major rules because, again, universal generalization requires that we replace every instantial letter with the variable that is in our quantifier. In this case, the variable in our quantifier is y. Therefore, we need to replace both of our instantial letters, both the x's, with a y, like we did over here on the left. So this over here on the left, good. This over here on the right, bad. Don't do it. Now we're going to look at existential instantiation. Now, unlike universal instantiation, I am not allowed to go from variable to variable. You must go from variable to constant. So remember how instantiation works. I remove a quantifier and I replace the bound variable with another instance. In this case, the instance has to be a constant. So look over here on the right side. This is not allowed. I'm not allowed to take this existential statement, remove the quantifier, and then replace this variable with another variable. I must replace this variable with a constant, like I have here. So you're not allowed to existentially instantiate to a variable. You must existentially instantiate to a constant. Further restriction, the existential name must be a new name that does not appear in any previous line, including the conclusion line. So this A right here, I'm not allowed to use it unless it's new. If there's an A on some other line or in my conclusion, then I cannot use it. So I can only use a new name that does not appear in any previous line or the conclusion itself. And I can only instantiate to a constant. So again, no instantiating from variable to variable, as is over here on the right side in the red. Only instantiating from variable to constant, as is done on the left. And don't forget your restriction. More on this in a little bit. So let's look at an example. All rockers are legends. Some rockers are sloppy people. Therefore, some sloppy people are legends. We can symbolize this as follows. For all x, if x is a rocker, then x is a legend. There exists an x such that x is a rocker and x is a sloppy person. Therefore, there exists an x such that x is a sloppy person and x is a legend. If both quantifiers can be removed, the conclusion can be derived via simplification, modus ponens, and conjunction. We can remove the quantifier on line 1 with ui, but in order to remove the quantifier on line 2, we will need to use ei, which is exactly what we're getting ready to show. So again, I see this right away. You may not. If you look at it for a minute, you may realize that you can derive this conclusion via simplification, modus ponens, and conjunction once we remove these quantifiers. If you don't see it now, you'll see it here when we do the example, okay? So here it is again. For all x, Rx implies Lx, and there exists an x such that x is R and x is S. Therefore, there exists an x such that x is S and x is L. So first things first, we're going to EI line 2. Now remember, I have to go from variable to constant when I EI. So I'm going to choose, I choose the letter D here. I could have chosen any of my constants. Further, remember my other restriction on EI. I have to use a new letter. This is why on line 4 I UI line 1 rather than doing this on line 3. Notice I could have UI'd on line 3. But if I would have done that, then I wouldn't be able to use the same letter for my EI. Right? Note, we did EI first due to the restriction that I must start with a new letter when I EI. So on line 3, when I EI'd line 2, remove the quantifier and replace these variables with constants, This is a new constant that doesn't occur anywhere prior nor in the conclusion. Okay? It's very important that I did it in this order. I could have UI'd on line 3, but had I done that, then I would not be able to use the same letter when I EI'd, which I ultimately need to do. Because what we're going to want to do here is simplify line 3 to get my RD. Now you should see that I have modus ponens lined up. RD into line 4 gives me LD. All right, so LD via 4-5 modus ponens. So first thing I did, EI'd line 2, UI'd line 1, simplified line 3 to get RD, then I used modus ponens. If RD, then LD. Well, I have RD, therefore I have LD. 4-5 modus ponens. Now my commutativity rule, I'm going to flip around line 3 to get SD and RD. This way I can simplify and get SD. Now hopefully you see the strategy here. I'm going to take line 6 and line 8 and I'm going to conjunct them. SD and LD. And then I can use my new rule, existential generalization, to re-quantify what I had on line 9 and go from a constant to a variable. Okay? So again, the important thing to take note of here is that I used EI first because I had to make sure that my letter was new. All right, had I done UI first, I wouldn't have been allowed to do that. So we did EI first, then UI. All right, once I remove these quantifiers, then I can just implement my rules of implication. Simplification of line 3, which allows me to do modus ponens with 4 and 5. Then I do commutativity on line 3 so that I can simplify and get SD. That way I can conjunct line 8 and line 6 to give me SD and LD, and then I just use the EG rule to re-quantify and go from constant to variable. And of course, this is exactly what I was looking for up here in my conclusion. Problem solved. Let's look at a few further examples. So in this case, I have 3 universal statements. I have premise 1 says for all x, if x is h, then x is L. For premise 2, for all x, if x is L, then x is h. And my conclusion for all x is h if and only if x is L. So you might guess the first thing we're going to want to do here is use UI. Again, in order to use my rules of implication, I need to remove the quantifier. This quantifier is governing the entire line on both premise 1 and premise 2. Therefore, I am not allowed to use any of my rules of implication on these. So I need to remove the quantifier first, which I do. Then I'm going to do the same thing to line 2. So I UI line 1, I UI line 2. And notice in this case I didn't even change the variable. You don't have to. If the variable, if x is what I want ultimately, I have no reason to change it to another variable, nor a constant in this case, particularly since I'm ultimately going to need a UG, which means I'm going to have to go to a variable. And since I'm not allowed to UG from a constant to a variable, it would make no sense for me to UI to a constant. Okay? So you got to think about all this stuff. Ultimately, since we want to derive a universal statement, we know we're going to have to end this statement with a UG more than likely. And if we have to end it with a UG, then we know we have to move from variable to variable. Therefore, when we UI, we don't want to use constants here. We want to use variables. Remember, again, your variables are lowercase x, y, and z. Your constants are letters A through W. So we want to use x, y, lowercase x, y, or z in this case because we're ultimately going to universally generalize later. So now at line 5, we're going to conjunct lines 3 and 4. And once we do this, we can use our rule of replacement equivalence. Remember, our rule of replacement for equivalence tells us that if I have a conjunction of 2 implications that are flipped, right? If hx then lx and if lx then hx, that's equivalent to hx if and only if lx. Remember, this stands for biconditional. So what it means is a conditional going both ways, which is exactly what's represented in 5. I have hx then lx and I have lx then hx. So that just means hx if and only if lx, or conversely you could say lx if and only hx. Okay? So from our handy-dandy rule of equivalence, we get that. Now, hopefully you see exactly what we're going to do on line 7, which is simply UG from line 6. We're going to add in our quantifier, which binds both of these variables in here. And voila, we've reached our conclusion. Note, I said this before, but I want to say it again. Because we want to perform a UG on the last line of the proof, we instantiate lines 1 and 2 using a variable, not a constant. Remember, we're not allowed to UG constants. Next example, premise 1. For all x, if x is a or x is b, then x is c. There exists an x such that x is a. Therefore, there exists an x such that x is c. So again, we can see that we can't use any of our rules of implication, so we're going to have to use our instantiation rules. Now you might guess that we ought to use EI first, because we know that if we use a constant, that it's got to be a new constant. And that's exactly what we'll do. So we will remove this quantifier, and we replace a variable with a constant, line 2 EI, and we did this first, again, because of our restriction. Notice on line 4 we're going to UI line 1, and we're going to use the same letter, the same constant that we use in 3. We do this intentionally so that we can now use our rule of implication. All right, hopefully you can see the move that we're going to make. If we use addition on line 3 to add a BM, we can now perform modus ponens on line 4. Right? The antecedent of line 4 is AM or BM, and the consequent is CM. On line 5, I have AM or BM, which of course is the antecedent for line 4. So modus ponens will allow me to derive a CM. And remember what we're trying to get at the end? We're trying to get there exists an x such that x is c. So all we got to do to line 6, you got it, existential generalization. So we quantify this, change the constant to the variable that is in the quantifier. Again, abracadabra, hocus pocus, we have our conclusion. But we need more. Yes, we do. I'm sure at this point you're probably like, how much more do we really need? Well, you definitely need a little bit more, and I'll show you why. Look at the following example. Notice, both premise 1 and premise 2 have tildes preceding the quantifiers. So the main operator in these statements is a negation. Neither statement can be instantiated, and if we can't instantiate them, then we can't derive the conclusion. Notice there's no rule implication that we can use for any of this. Okay? And I cannot instantiate because I can only instantiate when my quantifier governs the entire line. But in this case, it's the negation that is the main operator. Okay? So with the negation being the main operator, I'm not allowed to instantiate. I'm only allowed to instantiate on lines who, you can think of it this way, whose main operator is a quantifier. So here's a little note. This is important. We can only perform UG, UI, EG, and EI on whole lines, and we can only use our rules of implication on lines that do not have quantifiers governing the entire line. So I'm going to hopefully make this clear in a moment. Let's look at some examples. So look at this. I have, there exists an x such that x is p and x is not q, and for all x, x is r or x is q. What's the main operator for this statement? Hopefully you said conjunction. Notice, my main operator on this statement is located right here in the center, the dot. So this is considered a conjunction. Therefore, I can use my rule of implication on it. Now I want to make this clear. Remember, I am not allowed to use my rules of implication on lines where the quantifier governs the entire line. But notice the quantifier does not govern the entire line. This quantifier governs this. This quantifier governs this. But the main operator is the dot. So again, as I mentioned before, and I'll back up just for a second, I'm going to look at the bottom of this page. You might think of it as a case where the quantifier is the main operator. It is the only time we're not allowed to use our rules of implication. So if we look at this, the main operator is the dot. So I'm allowed to use my rules of implication here. Therefore, I can use simplification from line 1 to get this. But now look what I have at line 2. What's my main operator on line 2? It's the quantifier. In this case, my quantifier is governing across the entire statement. So I am not allowed to use rule of implication here. I could not simplify and get px out of this. Okay? So what can I do? I can EI, PA, and not QA. Remember with EI, I'm going to remove my quantifier and replace my variable with a constant. Now that I've done that, again, what's the main operator on line 3? It's the dot. This is a conjunction. Therefore, I'm allowed to use simplification if I want to. So here's the note to take away from this. Line 1's main operator is the dot, so we can use our rules of implication, but we cannot use EI, EG, UI, or UG. On line 2, the whole statement function is governed by the existential quantifier, so we can use EI on it, but we cannot use our rules of implication on it. So the easiest way to think about this is if my main operator is a quantifier, as in line 2, then I can do EI, EG, UI, or UG, but I cannot use my rules of implication. Okay? If my main operator is a quantifier, I cannot use my rules of implication. In contrast, if my main operator is not a quantifier, as in the case of line 1, where my main operator is the dot, then I am not allowed to use EI, EG, UI, or UG. Make sure that you study this particular example for a moment, okay? Pause the video if you need to, but you need to understand when you're allowed and when you're not allowed to use your rules of implication and your EI, EG, UI, and UG rules, okay? One more thing, and of course it's not the last thing, but it's at least one more thing. You can use rules of replacement on lines governed by a quantifier. Again, you can use rules of replacement on lines governed by a quantifier. So unlike rules of implication, rules of replacement can be used on lines governed by a quantifier. So for example, if I have for all x, it's not the case hx and gx. I am not allowed to use my rules of implication here. Why? Because this entire line is governed by this quantifier. And in essence, we can think of this quantifier as being the main operator. Okay? I am allowed to use UI, of course, right? But I'm also allowed to use my rules of replacement. So for instance, I can use De Morgan's here. Line 1 says for all x, it's not the case hx and gx. On line 2, by rule of De Morgan's, I am able to claim for all x, it's not the case hx or not the case gx. So again, notice, on lines where my quantifier governs the entire line, I am not allowed to use rules of implication, but I can use rules of replacement, and I can use my 4 new rules of inference, UI, EI, EG, or UG, depending on what applies. It's actually only going to be the U. In this case, only UI applies. If this was an existential quantifier, then only EI would apply. Okay? This, perfectly legal though. Rules of replacement, fine. So one last time, do not use rules of implication on lines where the quantifier governs the entire line. You can use rules of replacement on lines governed by a quantifier. So let's go back to the original example that we were looking at. I have premise 1. It's not the case that there exists an x such that that x is p and that x is not q. And then this says it's not the case that for all x, x is r or x is q. therefore there exists an X that's not P. We cannot instantiate any of the lines, and we cannot use any of our rules of implication, so we cannot derive the conclusion. So what do we need? We need another rule. And that will be Rule 5, which is quantifier exchange or change of quantifier rule. Notated as capital C, capital Q. So let's try and get straight on CQ. First thing I want to do is look at some logically equivalent expressions. So the first one to look at is this. This 4 dots, by the way, just mean logically equivalent. Okay? So what I have here on the left is for all x, fx. On the right, I have it's not the case that there exists an x that's not fx. These are logically equivalent statements. I'll explain more of that in detail in a moment, but let's look at the other 3. So all of these are logically equivalent. Not the case all x, fx is equivalent to there exists an x such that x is not f. There exists an x such that x is f is equivalent to it's not the case that for all x, not fx. And the last but not least, it's not the case that there exists an x that's fx is logically equivalent to for all x, not fx. Now I know this is probably pretty cloudy right now. It might sound like I'm speaking some sort of foreign language to you, but what I'm going to do is go through each one of these by itself and show you how they're logically equivalent. But for the moment, before I do that, I want to explain exactly what we're going to be doing with CQ. See, the notion is with CQ, what we can do is it kind of works like a rule of replacement a little bit. I can, if I have an all x fx, I can just switch it and replace it with it's not the case that there exists an x such that x is not f. Therefore, we'll be able to solve problems that we previously weren't able to solve. So backing up for just a second, remember this example. Notice, I can't use any of my rules of implication, nor can I instantiate any of this. So what will I need to do? Well, if I use my change of quantifier rule, it may allow me to instantiate and therefore be able to solve the problem. Okay, so let's go through each one of these right here one by one. First things first. For all x, fx is logically equivalent to it is not the case that there exists an x that is not fx. So let's look at the statement. Everything is fantastic. So let's make the F stand for fantastic. This is saying for all x, if x exists, then fx is fantastic, right? Everything is fantastic. For all x, x is fantastic. This statement says it is not the case that something is not fantastic, right? It's not the case that there exists an x such that x is not fantastic. So think about this for a second. If everything's fantastic, then it's also the case that there does not exist anything out there that is not fantastic. If everything in the universe is fantastic, then there cannot be one single thing that exists in the universe that is not fantastic. So we can substitute the statement for all x, fx with the statement it's not the case that there exists an x such that x is not f, and vice versa, because they are logically equivalent. So think about it again. This statement is just telling me, this existential statement is telling me it's not the case that there exists an x, right, that is not fantastic, which is the same thing that's being said by the universal statement. So let's back it up for a second. Again, the universal statement's telling me for all x, x is fantastic, or in other words, everything is fantastic. The existential statement is telling me it's not the case that there exists an x that is not fantastic. So in other words, it's not the case that something is not fantastic, which of course follows. If everything is fantastic, then of course there is not one single thing that exists that is not fantastic. So these two are logically equivalent. Therefore, we can interchange them back and forth. So I can take an all x fx and change it to a not the case there exists an x such that x is not f. And I can take the existential statement and or the negated existential statement, I should say, and replace it with this universal statement. We'll do some examples towards the end. So let's look at the next one. Of course, this one's saying it's not the case that for all x, xf is equivalent to there exists an x such that x is not f. So again, it is not the case that everything is fantastic. Notice, let's back it up again for a second. Right here, right, everything is fantastic. So if I put a negation right here in front of this universal, it'll be telling me that not everything is fantastic. All right? So let's go look at it. It is not the case that everything is fantastic. Now think about it for a second. If it's not the case that everything is fantastic, what does that mean? Well, it means there's at least one thing out there that's not fantastic. There is something that is not fantastic, which is exactly what this existential statement says. There exists an x such that x is not f. If f means fantastic, then what we're saying is there exists an x such that x is not fantastic, which is logically equivalent to this. It is not the case that everything is fantastic. So think about it. If it is not the case that everything in the universe is fantastic, then it is the case that at least one thing that exists in the universe is not fantastic. Therefore, we can substitute the statement, it is not the case that for all x, fx, with the statement, there exists an x such that it's not fx, and vice versa, because they're logically equivalent. Next, there exists an x such that x is f is logically equivalent to it is not the case that for all x, x is not f. So again, let's look at it this way. This is telling me there's something out there that's fantastic. There exists an x such that x is fantastic. So there's at least one thing in the universe that's fantastic, which of course is equivalent to the claim it is not the case that everything is not fantastic. Now I know the double negation gets kind of weird here, but think about what it's saying. It's telling us that it's not the case that everything is not fantastic. All right? That would mean that it is the case that something is fantastic. Right? If it's not the case that everything is not fantastic, then it must be the case that there's at least one thing that's fantastic. All it takes is for one thing in the universe to exist that's fantastic for this to be the case. If I have one single thing in the universe that is fantastic, then it is not the case that everything is not fantastic. So again, think about what's being said. If it is the case that there exists something in the universe that is fantastic, then it is not the case that everything that exists in the universe is not fantastic. So we can substitute the statement, there exists an x such that it's fx, with the statement that it's not the case for all x, not fx, and vice versa, because they are logically equivalent. I hope you're beginning to see the pattern that's going on here. All right, so last but not least of these, I have it's not the case that there exists an x such that it's fx is logically equivalent to for all x, x is not f. So if we look at the way it breaks down in English, what we're saying is it's not the case that something is fantastic. Right? There does not exist a single x that x is fantastic. In other words, it is not the case that there is something in the universe that's fantastic, which of course means everything is not fantastic. There's not one single thing in the universe that is fantastic. Right? This says for all x, x is not fantastic. So for everything that exists, it is not fantastic. Whereas in this case, I'm saying there exists no such thing that is fantastic. So think about what's being said. If it is not the case that there exists something in the universe that is fantastic, then it is the case that everything is not fantastic, right? Because if there was even one thing in the universe that was fantastic, then that would mean it's not the case that everything is not fantastic, okay? So here again, if it is not the case that there exists something in the universe that is fantastic, then it is the case that everything is not fantastic. So again, we can substitute these statements with each other one way or the other. For all x, not fx is equivalent to it is not the case that there exists an x such that it's f. All right? This is telling me that it is not the case that there is a single thing out there that is fantastic, and this is telling me that everything that exists is not fantastic. So they are logically equivalent. So let's go back to the example that was causing us problems in the beginning. we're going to take a look at the proof. Again, premise 1 was a negation, premise 2 was a negation, and premise 3 is an existentially quantified negation. So we realize we can't use any of our rules of implication, right, because none of them apply, and we can't use EI, UI, EG, or UG because none of them apply. So we've got to find something to do. Well, what can we do? We're ultimately going to use our change of quantifier rule. So first things first, line 1, CQ. Remember, not the case that there exists an X such that X is P and X is not Q is logically equivalent to the claim that for all X, it is not the case PX and not QX. All right, these are logically equivalent statements. All right, this is telling me that there doesn't exist one single instance of this, of PX and not QX. All right, look at number 1. There does not exist one single instance where PX and not QX. So that means that for everything that exists, it's not the case PX and not QX. So by using quantifier exchange or change of quantifier rule, we can convert this to this. Now notice, now that I've done that, I'm able to use universal instantiation. But I won't do that just yet. First things first, let's CQ line 2 also. So line 2 says it's not the case that for all X, not Rx or Qx, and that's logically equivalent to the claim that there exists an X such that it's not the case, not Rx or Qx. Now, I know this might sound a little bit fuzzy right now, but go back, review your quantifier exchange rules, and you'll see, okay? Now that I've used change of quantifier on 1 and 2, I'm fully able to use my UIs and EIs. So that's exactly what I'll do. I will EI line 4. Now remember, one of the reasons why I'm going to EI first, because I could have UI'd line 3 first if I wanted to, but I'm going to EI first because of my restriction. I have to make sure that whatever constant I'm using is brand new and never been used before. So I can EI line 4. I'll remove my quantifier. I'll replace all my variables with a constant, which I've done. Then I will now UI line 3. I will remove my quantifier on line 3 and I will replace the variables with a constant. And of course I'm going to use the same constant as I used in line 5 so that I can now perform other operations on it. But again, I wanted to make sure I EI'd first because I have to introduce a new letter when I EI. Now look over here at the conclusion for a second. We know that we want to get there is an X such that X is not P. So it looks like we'll ultimately have to end this proof with an EG because we're going to have to reintroduce the existential quantifier. So we're probably, the move we're going to want to make is to try and get a P by itself or a PX by itself, or not PX by itself, and then add the quantifier, okay? Now if we look at line 6, we can see that we have a PA here. Now if we do some De Morgans, we can probably manage to get this out of there, but let's see how this works. First things first, we'll De Morgans line 5. So not the case, not RA or QA is equivalent to not RA and not QA via the rule De Morgans. Now I'll double negate to get rid of this double negation because remember not RA is simply equivalent to RA by rule of double negation. So once we double negate we get RA and not QA. Now we'll De Morgan 6 to get not PA or not QA. Remember our De Morgan's rules. 6 and 9 are equivalent to each other. Therefore, I can change this conjunct, right? The negated conjunct turns into negation, disjunct, negation via the rule De Morgan's. Then we'll double negate this as well because not QA is just equivalent to QA. So we end up with not PA or QA via line 9 double negation. Now you might see something. Look at line 8. If you look at line 8, you'll see, but if we simplify line 8, then it looks like we may be able to use disjunctive syllogism on line 10. But of course, before we can simplify line 8, we got to do commutativity. So we do commutativity on line 8 to flip it around, right, to give us not QA and RA. which thus allows us to simplify to get the not QA. Now look at line 10. I have not PA or QA. Right now I have not QA. So after we do commutativity on line 10 to get QA or not PA, we can then take this not QA, plug it in, get not PA. Right? Because line 13 says I have QA or not PA. Line 12 says not QA, therefore we know not PA. Via disjunctive syllogism, 12 and 13, which now we can just simply go up to our conclusion here. We know what we need. See it? We need to existentially generalize. And that's exactly what we'll do. We're allowed to go from constant to variable with EG. So we go from not the case PA to there exists an X such that that X is not P. Notice this is completely legal and it makes common sense if you think about it. Remember, this is a singular statement, so it's telling me that A, which is a person, place, or thing, so again, let's think of it as Adam, and P is our predicate word, so let's say punk or something. Adam is not a punk, is what 14 says. So if Adam's not a punk, then that means there exists at least one thing in the universe that's not a punk. Mainly Adam. We know that for sure. There might be other ones, but at least Adam. Therefore, we're able to solve for our conclusion. Now, I hope that this helps. In the next video, I'm going to do more examples of proof using all of the rules. But for right now, focus on getting straight on UI, UG, EI, EG, and CQ. Recognize when and when you cannot use them. Try and get your restrictions in line, and make sure that you also understand when and when not to use implication and rules of replacement. Just as a little follow-up, you're allowed to use rules of replacement on lines that are governed by quantifiers. You are not allowed to use rules of implication on lines governed by quantifiers. So again, if we look at line 3 here, we are not allowed to use our rules of implication on that. Okay? But we are allowed to UI it, which we did. And actually, if we wanted to, we could have done De Morgan's on it. All right, notice how on line 6, we UI'd line 3, and on line 9, we De Morgan's line 6. We could have actually done this the other way around. We could have gone to line 3. We could have De Morgan's line 3 first, and then we could have UI'd it. So again, rules of replacement can be used on lines that are governed by quantifiers, but rules of implication cannot. EI, UI, EG, and UG cannot be used on lines, or let me restate this. EI and UI cannot be used on lines that are don't have a quantifier as governing the entire line. So let me re-say that. EI and UI cannot be used on lines that do not have a quantifier governing the whole line. So on line 4, we see that this existential quantifier is governing the whole line. Therefore, we can use EI. You can't use UI on this, but you can use EI on it. On line 3, I have a universal quantifier governing the whole line, so I can use UI here. But I cannot use rules of implication on either one of these. Okay? Rules of implication can only be used when my main operator is either a negation, a disjunct, a conjunct, a conditional, or a biconditional, or one of these things. Alright, I hope this helps. Again, I'll be doing another video soon where I just simply do proofs using all of our new rules and the previous 18 rules that we already have. I hope that you guys are understanding this. I know that it's not the easiest material to learn via an online class, but work hard. I think you'll get it. Okay, everybody. Peace.